Okay, so this is going to be a video on some basic set theory definitions and notations. You might have seen some of these already. Some of these might be new for you. But either way, I want everybody to be on the same page. So here we go. Okay, so when we say a set is a collection of some, some distinct objects with a precise description of providing a way to decide if an element is part of the set or not part of the set. The things that are in the set is called elements or members. Okay, so and this is how we write it. So if I write X belongs to A, right? So this symbol, membership symbol, looks like a lowercase e with maybe the loopy part cut off. So if you put that between an object and a set, this means that X is part of the set. So X is inside the set A. If you want to show that something doesn't belong to a set, you might write it this way. You write X belongs to A, but then with a slash through it showing that it does not belong to that set. Okay. So here's some examples. So there are several different ways where you can write the set. So you usually use curly braces to denote a set. And sometimes you can list all the members of the set. So the set A here has two elements, the two numbers 1 and 2. So you might list out all the elements separated by comma. Another way you could describe a set is using a set builder notation. So this is an example there. So set B, and opening curly braces. So the left-hand side of the column tells you the expression of what is in the set. So it's talking about X, which is a real number that's in the set. And the right-hand side of the column tells you what condition you have to meet for you to belong to the set. So if the absolute value of X is less than or equal to 1, so any real number where the absolute value is between 0 and 1, or if X is between -1 and +1, then you're within the set B. So another way to, if you're familiar with interval notation, is all the number between -1 and +1, including the endpoints. So both of these are describing the exact same set. Here's another set. So this set consists of only one member, the number pi. So these are sometimes called Singleton set if it only has one element. I want to make a distinction between the number pi and a set that's containing the number pi. So these two are different things, right? So on the left-hand side, you treat it as a number. The right-hand side is a set containing that one number pi, right? So they are different. Okay. It is possible to have infinitely many objects within a set. Right? I guess B was already an example of that. But this is an object that we're gonna work very closely with this quarter. N stands for natural numbers. And it's basically the numbers you use to count. So starting with 1, 2, 3, 4, 5, and so on. So all of the positive integers the numbers you use to count that set is called natural numbers. There's a little bit of inconsistency on how people define this set. Some textbook might define the natural numbers starting with number 0, so 0, 1, 2, 3, and so on. Most math books will start with number 1. So I'm just going to stick to the definition that our textbook gives. So we'll start the natural numbers with starting with the lowest number 1. But either way, it's fine. You just have to stick to the same convention, right? So that's what we'll do. So notice if the pattern is clear, you could just put ... to indicate and so on. So that's totally fine as long as the pattern you're expressing is not ambiguous. The letter Z usually denotes the set of integers. So that includes the number 0 and all the negative numbers as well. So 0, 1, -1, 2, -2, 3, -3, all of those are part of the integer set. And the letter Z is used, I think that's because some German word for integers involves Z. By the way, these font that I'm using when I write these, this is called Blackboard font. When you're typing and you want to use these, if this font is not available in your word processor, you could just use bolded N or bolded Z, and that's close enough. Okay. All right. So I want to be able to compare different sets. So one way to compare is to say that one set is bigger than another set. So if every element in one set, let's say A, also belongs to a bigger set B, then we say A is a subset of B. Okay, and this is the notation we're going to use. It looks like less than or equal to symbol, but the angle part is rounded, right? This is another notation that people use that also means the subset. Sometimes people put not equal to below it to show that it's maybe a proper subset, like it's subset but not equal to. That's another common thing that sometimes people use. Okay, but in our class, we'll use this notation. Okay. And when we have A is a subset of a B and B is a subset of A, so you could flip the symbol with a mirror reflection and say A contains every element in set B. Sometimes people use the word superset to say that. So if A is a subset of B and A is also a superset of B, so everything in A is also in B and everything in B is also in A, then we say the two sets are equal, right? So that means that the name you give to a set doesn't really matter. The only thing that it really defines a set is what's contained inside of it. Okay. So, for example, if I say A is a set that's consisting of 1 and 2, I could have equivalently written A is a set consisting of 2 and 1. Order does not matter. Also, repetition is not a thing in a set, so it's either it contains the member or it does not. So if I write a set 1, 2, 2, me repeating the membership of 2 does not really matter, right? So this is exactly the same set. It's a set of two distinct elements, 1 and 2. So repetition is not a thing that you keep track of within a set. Okay, so that's what I meant by double membership is not a thing. Okay. Also, how you decide to write the description, if you're using a set builder notation like B, right? I could describe it this way, or I could describe it this way. It might not be clear right off the set, right at the outset that it might be describing the same set, but the actual description you use does not matter. If it described the same membership of elements, it is considered the same set. Okay. And this gives us a way to how to prove two sets are equal. So if you want to show if two sets are equal, you could do it in 2 steps. You could say that one set, every member of one set is contained in the other, and vice versa. So you could show that the 2 sets are equal that way. I'll do an example of this in a bit. Okay. Another set that we'll talk about in this class is set of rational numbers. We usually use the Blackboard font Q for this. So any number P divided by Q, where P and Q are integers, such that the denominator is not 0. So any real number that could be written this way is considered a rational number. I think Q is for quotient. Okay, so we have this natural subset ordering. So natural numbers is contained within integers, and both natural numbers and integers are contained in rational numbers, and rational numbers are contained within real numbers. Okay. I should mention that you could have a set that has no membership whatsoever. So what's called an empty set is usually denoted with a circle with a diagonal slash through that circle. So that's the notation we'll use with set of no elements. So you could write it this way if you want, curly braces with nothing inside of it. I should also mention that this might be confusing, but it's important to make the distinction. Empty set is different from a set that's containing an empty set. So the set with nothing in it is not the same. You could have a set with an empty set inside of it. So that set is not, on the right-hand side, is not empty. It has one element, and that element is the empty set, right? So that's different from the empty set itself. I hope that makes sense. You could, if you want, you could imagine empty set being like a bowl with nothing in it. So on the left-hand side, this is a bowl of nothing. On the right-hand side, there's an empty bowl inside of a bigger bowl, right? So that's different, right? Empty bowl is different from a bowl that's sitting inside of a bigger bowl. Okay. Oops. Okay. All right, so we're going to use the term proper subset for subset that's not the set itself. So it turns out that every set is a subset of itself because anything in A is of course contained in A. But if you really want to describe a set that's actually smaller than the set you're talking about, then you could say, oh, you can make the distinction by saying it's a proper subset. This is strictly smaller. Okay. Another term that I want you to know is what's called the power set. So power set of some set A is set of all possible subsets of that set A, right? So the notation we're going to use is script P for power set of A. Sometimes people use 2 to the exponent of the set A. Okay, so for example, the power set of the set that consisting of 1 and 2. So there's 4 possible subsets here. Empty set is always a subset of any set. You could have a singleton set of 1 and 2. And you could also have the full set, 1 and 2. And these are all 4 possible subsets of this set 1 and 2. Notice how this is a set of 2 elements, and the power set has 2 to the 2 elements, right? 4 elements. That's the reason why people use this notation for power set. Okay. So let me prove some things. Let's say I have 2 sets that's described in 2 different ways. So they're both using the set builder notation. So any real number x such that x squared is less than x, or the other set t is any real number between 0 and 1. So this is the interval from 0 to 1, not including the endpoints. And because I want to prove things, let's say I want to prove that S as a set is equal to the set T. Let's prove this. So I'm going to prove this in 2 steps. So I want to show that they contain the same elements, S and T. So first, I will show that anything in the set S is also, set is contained in the set T. Then I will show that everything in T is also included in S, right? So if I show that S is a subset of T and T is a subset of S, then they have to be equal to each other. We talked about that earlier. So how do I show that S is a subset of T? Okay. Okay. So what we could do is we could pick any element in S. So let's say let X belong to S. So I look at an element in S. I want to show that this description implies that he satisfies this description for T. Okay. So then we know that, square of any real number is not negative. So any x squared is greater than or equal to 0. Also, by the description of the set S, that x is always greater than x squared. Oops. I just want to say that x is greater than x squared. Okay. This means that 0 is less than x. So that completes the first half of the description. 0 is less than x. Also, if we start with the expression x squared is less than x, that we know that that's true from the description of the set S. So if we take this and divide both sides by x, we could get x is less than 1, right? If I divide the left-hand side by x, I get x. And if I divide the right-hand side x by x, I get 1. X divided by x is 1. And the inequality in the middle here, this does not change because I divided by a positive number. And also, division makes sense because I did not divide by 0, right? We know we didn't divide by 0 because we know x is greater than 0. It's a positive number. Okay, so what did we show? We have shown that 0 is less than x and x is less than 1. So those two things combined show that 0 is less than x and x is less than y. So x belongs to t as well. So we started with x in S, and we've shown that x satisfies the criteria for the t to belong to that set. Okay, since x in S was arbitrary, S is a subset of T. Yeah, it could have been any element in S, and the same argument will show that it also belongs to T. Okay, so we've shown the first half. S is a subset of T. Okay, now let's let Y be an element of T. Okay, so this means that this element Y is somewhere between 0 and 1. Okay. If we multiply both sides by Y, both sides of Y less than 1 by Y, we get Y squared is less than Y. Also, I do not have to flip the inequality because I multiply by a positive number, right? I know that Y is greater than 0. Okay, but Y squared being less than Y is exactly the condition we need to show that it belongs to set S. Okay. Therefore, Y also belongs to S. Okay. Y was arbitrary element of T. So any element of T is also an element of S. So T is a subset of S. Okay. So we've shown that S is less than or equal to T. Sorry, S is a subset of T, and T is a subset of S. Therefore, S is equal to the set T. I hope that made sense. All right. I have a few more definitions that we're going to use often in this class. So as far as talking about sets of subsets of integers, um, we call a number even if it could be written as 2 times an integer, where k is any integer. The odd numbers, any number that could be written as 2 times an integer plus 1. So if you can write it in this form, then it belongs to set of odd numbers. So that's fairly common. I'm sure you've heard of even and odd numbers, but this is precise definitions that we're going to use for this class. And I don't know how common this notation is, but it's a useful one, so we'll use it. So if I write square brackets of n, this is all of the integers 1 through n. Okay. And another term that's related to even or odd integers is the word called parity. So if I ask for parity of an integer, then it's asking for, is it an even integer or odd integer? So some arguments will break down into breaking it into even integer case and odd integer case. So this is a useful terminology to know. Okay. And I hope you've seen an integer, like an interval, sorry, not integer, interval notation for subsets of real numbers. So if I use rounded parentheses, then this talks about all of the real numbers strictly between two numbers, a and b, not including the endpoints. If I use the square brackets, that means please do include the endpoints a and b. Okay. You could have half open and half closed interval as well. So if I use a square bracket for the a, that means include that endpoint a in the set. But the rounded parentheses means do not include that endpoint. Okay. You could have sets interval going off to infinity. So if I write something like this, it means any real number that's bigger than or equal to a, and there's no restriction on the upper end, right? But when you do write infinity here, you never include infinity as a subset of real number, because infinity is not really a number. It's just a direction on the number line. Okay. And you could do something similar with the lower endpoint of the interval as well. So if you talk about all of the numbers between negative infinity to infinity, that's all real numbers. So that's equivalent to talking about the real numbers are. Okay. All right. If you have a subset of real numbers, sometimes there's a maximum of the subset. So when I say a maximum of a set, it's a member that's at least as large as every other member in that set. So if X is a maximum of S, it has to satisfy two things. First of all, X have to belong to the set itself. And if you pick any other element in the set, including X itself, it's at least as large as that number. Okay, so for example, let's have a concrete example. So if I have an interval that looks like this, so let's call that set S, then 3 is maximum of S. Okay. But if I had an interval like 1 to 3, not including 3, then this doesn't have maximum. Because you want to say 3, but 3 does not belong to the set because of the rounded parentheses. So some sets do not have maximum, and that's okay. Okay. All right. Another useful definition to have is a list of things. So opposed to sets where the order does not matter and you cannot have double membership in a set. When you talk about a list, you could have, so order matters and you could have double membership. So what I mean by that is this is an example of a list, 1, 5, 2, 4. This is 4 tuple. And this is different. I want to give myself more room, but when you're talking about a list, order matters. So 1, 5, 2, 4 is different from 5, 1, 2, 4 because 1 and 5 is flipped in order. Okay. And you could also have repetition. So 1, 1, 2, 4 is different from 1, 2, 4. So having 1 twice doesn't make a difference. Opposed to in a set, double membership does not make a difference because it already belongs to it. Okay. If you have 2 sets, you could write down what's called a Cartesian product. So A cross B is all tuples where the first coordinate x belongs to the first set A, and the second coordinate y belongs to set B. Okay, and you could write exponents of a set as well. So if I write a squared, that means it's a Cartesian product of the set A crossed with itself. Or you could have a larger exponent if you like. Okay. So r squared is called Cartesian plane. So this is the x and y coordinates that you usually draw when you draw a graph, right? Okay. Notice the notation for ordered pair or 2 tuple is exactly the same as intervals where left and the right endpoints are not included. So this is kind of unfortunate. But if I write 1, 2 with rounded parentheses, this could mean 2 tuple, or it could also mean interval subset of real numbers where it's all the numbers between 1 and 2. Okay, so this is an element of r squared. This is an interval of one-dimensional real line r. So notation is exactly the same. We just have to be able to distinguish it from context. So that's too bad. Okay. All right, a little bit more to go. If you have 2 sets A and B, we could talk about their union. So if I write A with this symbol that looks a little bit like a U, but you usually have a vertical bar at the right end. If it looks like an A cup B, this consists of all the elements inside of A or B or both. So you just kind of dump together what's in A and B together. And if it doubles up, you still keep it in the union. Okay, so that's the union of two sets. So you can make a bigger sets this way. Another way to make a new set is called intersection. So if you use an upside down union symbol, so A intersect B consists of all the elements that are in both A and B at the same time, right? So that's the intersection. So this, you create like a smaller set, right? By looking only at the double ups between A and B. Okay. Another common notation that we're going to use is called complement. So if I write C in the exponent of the superscript of A, that means all of the elements that's not in A. But this really only makes sense if you kind of determine what is it a part of. So if you're looking at it as a real number, then it's all the real number that's not in the set A. But that might be different from looking at a complement if you look at it as being part of a different bigger set, right? So complement only makes sense when the universe of discussion is clear from the context. Okay. There's another notation, set difference, A minus B. Sometimes this is written A backslash B. That's another common notation. This consists of all the set in A that is not in B. So another way to write that is intersect A with everything that's not in B. Okay, so that's how you can talk about a set difference. Okay, and I'm a visual person, so when you want to try to kind of brainstorm how to prove things when you're talking about sets, one way to visualize it is what's called Venn diagram. So you could think of A and B and elements being inside of A inside of this circle. And you could talk about things that are in both A and B. You could talk about things that's in A and not in B, and things that are outside of both A and B, and so on. So drawing from these concepts with Venn diagram, if I'm talking about union of A and B, that talks about everything inside of A, everything inside of B, and everything inside of both, right? So all of the shaded area corresponds to A union B. If I'm talking about the intersection, I'm only talking about this bit. So everything that's both in A and B at the same time. That's a smaller set. If I'm talking about complement of A, that's everything that's not inside of A. So if I just shade everything outside of the set A, that's the complement of A. If I'm talking about a set difference, so everything in A that's outside of B, that would be the shaded portion of our set difference of A minus B. Okay. All right. That's enough for today. I'll see you on Thursday.